If you want to build a more self-sufficient home, then understanding how to reduce your dependence on mechanical cooling is a critical step toward energy independence. In the average American household, cooling accounts for roughly 20% of all electricity consumed, representing a huge burden on energy consumption and financial costs. On this channel, I've discussed a lot of passive cooling techniques, but never explained how to tie these together to build an entire system that has the potential to cool your entire home using nothing more than the principles of nature. In the next few minutes, we're going to cover the 3 critical steps that create an effective passive cooling system and the techniques you can implement right now that can reduce indoor temperatures by as much as 15 degrees Fahrenheit and cut your bills by over 40% without using a single watt of electricity. But before we get into the methods, it's important to understand what passive cooling actually is, where it came from, and, more importantly, why it matters. Many of the techniques we are about to explore are time-tested, based on principles that ancient civilizations relied on for thousands of years before the advent of mechanical cooling. Passive cooling is a collection of methods used to control the temperature of interior spaces that have been evolving and developing for thousands of years across every civilization that has walked the planet. Persian engineers built wind towers in the deserts of Yazd over 2,500 years ago on the principles of downdrafts. Egyptians used evaporative cooling by hanging weavings in doorways, and across the Middle East, courtyard homes combined shading, thermal mass, evaporation, and a myriad of other techniques to create integrated cooling systems that kept interiors comfortable through extreme desert heat long before electrical air conditioning units existed. Passive cooling is a crucial tool that's been evolving for millennia, yet even now it still has benefits that no modern mechanical systems can compete with. One of the most obvious advantages of passive cooling is its impact on energy consumption. By reducing reliance on mechanical cooling systems, buildings can significantly lower energy bills and reduce greenhouse gas emissions, providing both environmental sustainability and long-term financial benefits. But it can also improve indoor air quality. Natural ventilation encourages the exchange of stale indoor air with fresh outdoor air, reducing the concentration of pollutants. The absence of noisy, energy-intensive equipment creates quieter, more comfortable spaces. And occupants enjoy a stable, naturally regulated indoor environment, which studies have shown can enhance productivity in workplaces and overall well-being in residential settings. Rather than utilizing active electricity to generate cold air, passive designs control the entry, movement, and dissipation of heat energy through 3 fundamental physical mechanisms: heat control, heat reduction, and heat removal. Heat control blocks solar and conductive heat before it enters the building envelope. Heat reduction lowers the temperature of the air and surfaces surrounding the building. And heat removal dissipates built-up indoor heat to natural environmental heat sinks. These 3 mechanisms work in unison with one another, and together they can create a highly effective passive cooling system. When building yours, it's important to consider each of these 3 pillars, as prioritizing one over the other can have a detrimental impact on the cooling efficiency of your home. Following these 3 mechanisms, we're going to run down the most efficient and cost-effective ways you can build a complete passive cooling system for both new builds as well as cost-effective modifications you can implement right now for immediate benefits to your home. At the end, I'll show you the easiest, most cost-effective combination of all these techniques that costs little more than a few $1,000s and can immediately reduce your cooling bill by as much as 40%. Let's get started. Mechanism 1. Heat control. Heat control is the first step to building an effective passive cooling system. These are techniques designed to block heat from entering a building envelope. The first technique we can utilize for heat control is shading, especially in areas that contribute the highest unwanted heat gain, like windows. The United States Department of Energy estimates that around 76% of the sunlight that falls on a standard double-pane window enters your home as heat, and windows alone account for 25 to 30% of residential heating and cooling energy that is lost. But if you stop that solar radiation before it hits the glass, you eliminate the problem at the source. For existing buildings, exterior awnings are one of the most effective and accessible options to fix this problem. The Department of Energy reports that awnings reduce solar heat gain by 65% on south-facing windows and 77% on west-facing windows. Alternatively, solar screens are also a great option. Solar screens and exterior roller shades block 70 to 90% of solar radiation before it touches the glass. But there's an important distinction between these and interior blinds. The Department of Energy explicitly identifies exterior coverings as significantly more effective than interior alternatives because absorbed heat stays outside the glass rather than radiating into the room. Exterior shutters are also another option when it comes to thermal management. Louvered shutters in particular are highly effective at reducing solar heat gain by blocking direct sunlight before it hits the glass, reducing heat transfer by 20 to 60%. Operable louvers provide adjustable shade, privacy, and airflow. And when closed, shutters trap a pocket of still air between the panel and the window, creating a natural insulating barrier. The same principle as double glazing. Wood shutters achieve R values of 3.5 to 4 per inch of thickness, while composite shutters sit at 2.5 to 3 per inch. Providing your home is well insulated, keeping your shutters closed during the heat of the day and opening them as evening temperatures drop is one of the simplest and most effective thermal management strategies available. Reflecting is the next technique for managing heat control, and the biggest win here starts with the part of your home that is exposed to the most sunlight: the roof. A conventional dark roof absorbs 85 to 95% of the sunlight that hits it, and on a hot day, that surface can reach 150 to 175 degrees Fahrenheit. A cool roof, on the other hand, one engineered to reflect 65 to 90% of solar radiation and emit absorbed heat as long-wave infrared, typically stays within about 27 degrees of ambient air temperature. This works on the albedo principle, a surface's ability to reflect sunlight, and the impact that can have on your cooling demands is huge. Lawrence Berkeley National Laboratory data shows cooling energy savings of 17 to 39% of the treated roof area's contribution, while Argonne National Laboratory's modeling of a Chicago heatwave scenario found cool roofs cut air conditioning demand by 16%, outperforming both green and solar panel-covered roofs. For existing homes looking to incorporate this into their structures, the cheapest retrofit is a liquid elastomeric or acrylic paint coating applied directly over an existing low-slope roof. The cost of this runs between 75 cents and $2.50 per square foot, with a roughly 10-year service life. The winter heating penalty that critics raise has been addressed by multiple Department of Energy, Princeton, and Lawrence Berkeley studies, all confirming net annual savings even in cold climates. And this same principle of reflecting heat from your roof can also be applied to your windows. High reflectivity films can lower the solar heat gain coefficient of a clear single-pane window from as high as 0.87 to as low as 0.22, rejecting 70 to 85% of total solar energy. The cost runs $8 to $15 per square foot installed, with a payback period of 2 to 4 years. A comprehensive study modeled across multiple climate zones found that a low-E film retrofitted to clear single-pane glass yielded an average of 29% HVAC energy savings. And unlike standard tinted films, low emissivity variants also reflect interior radiant heat back into the building during winter, which reduces the seasonal heating penalty. But keep in mind that any solar-treated window will reduce sunlight in both seasons, so if you rely on passive solar heating in winter, the trade-off should be considered carefully. Another critical part of effective heat control is insulation and a radiant barrier. A radiant barrier is a reflective aluminum foil stapled to the attic rafters, which can reduce the heat flowing through the attic floor by an additional 33 to 50%. Oak Ridge National Laboratory field tests on R19 attics showed summer ceiling heat flux reductions of nearly 50% for foil stapled directly to rafters, translating to 5 to 12% cooling cost savings in warm climates. The material cost is 10 to 50 cents per square foot for a do-it-yourself install, or 50 cents to $1.50 professionally installed. One critical design flaw to avoid with a radiant barrier is to never lay foil directly on top of attic floor insulation, which can trap moisture, accumulate dust, and lose its reflectivity. A radiant barrier is a key piece of the puzzle, but so is good insulation. Effective insulation does not just keep heat in during winter, it keeps it out in summer too. Think of it like a cooler box. The same barrier that prevents cold from escaping also prevents heat from entering. Without adequate attic insulation, a residential attic can reach 140 to 160 degrees Fahrenheit in summer, That heat conducts straight through the ceiling into your living space. The Department of Energy recommends attic insulation levels of R49 to R60 in colder climate zones and R30 to R49 in warmer ones. Bringing an under-insulated attic up to current code with blown-in cellulose or fiberglass costs $1 to $3 per square foot, typically $500 to $1,500 for an average attic, with a payback period of 3 to 7 years. Attic insulation can be a big win, and the Department of Energy has even called this the single most cost-effective intervention in any climate. But there's an important caveat here. If insulation is installed without adequate shading, built-up heat from solar gain through windows can be trapped inside the building, creating what is effectively an oven effect. So, insulation must work in combination with reflecting and shading, as well as the other techniques we're about to cover. Mechanism 2. Heat reduction. Once you have a plan on how to control heat from entering your home, the next priority is an effective strategy for creating a cooler microclimate around the building. And the best way to achieve this is with some strategic landscaping. Deciduous shade trees are the cheapest air conditioning system ever invented, and they do more than just block sunlight. A mature tree cools its surroundings through evapotranspiration, a process that releases water vapor from the leaves and absorbs latent heat from the air in the process. And the impact this can have on both energy saving and home temperatures is massive. A single mature tree, through transpiration alone, can offset the equivalent of 250 to 650 kilowatt hours of air conditioning annually. A study published in Energy and Buildings measured 2 Sacramento homes with newly planted shade trees and found seasonal cooling energy savings of 30%, an average daily reduction of 3.6 to 4.8 kilowatt hours, with peak demand reductions of 27 to 42%. But the cooling benefit of strategic landscaping extends beyond individual trees. Ground cover plants keep surface and ground temperatures significantly lower than hard paving, and on hot, sunny days, wet grass can reduce surrounding ground temperature by approximately 11 to 14 degrees Fahrenheit compared to dry, bare soil. And replacing dark asphalt paths and patios with light-colored pavers or dense low-water vegetation reduces conducted heat and ambient temperatures by approximately 2 to 5 degrees Fahrenheit in modeled neighborhoods. At the wider urban scale, researchers at Lawrence Berkeley found that mitigating heat island effects through strategic landscaping and light surfaces can cut United States air conditioning energy usage by 20% and save over $10 billion annually. But vegetation shouldn't be the only focus of a well-planned heat-reducing landscape. The presence of water features near a building can provide a significant cooling effect on the microclimate. A 2024 study of a Seville courtyard found that an open water feature, combined with misting, achieved a massive 22-degree Fahrenheit reduction in mean radiant temperature during a heat wave. A more engineered example of a water feature utilizing evaporative cooling is the Cool Ant beehive system designed by Ant Studio in New Delhi. Inspired by the geometry of a beehive, the system stacks cylindrical terracotta cones in a circular steel frame. Recycled water at room temperature runs over the surface of the porous cones, and as hot air passes through, evaporative cooling drops the temperature by approximately 11 to 14 degrees Fahrenheit. Evaporative cooling is a powerful tool for a passive system, although it only works effectively when ambient relative humidity is below roughly 60%. In hot and humid climates like Miami, Houston, or New Orleans, the air is already too saturated for meaningful evaporation. Mechanism 3. Heat removal. So by this point, we have reduced the ambient air temperature around the building and blocked or reflected as much heat as possible. Yet no matter how efficient your system is, some heat will always get through. So the final pillar of an effective passive cooling strategy is to move accumulated internal heat out of the building and into a natural sink like the ground or sky. And one of the easiest ways to do this is by incorporating the thermal mass into your build. Heavy materials like concrete, masonry, adobe, brick, stone, and water have high heat capacity. They absorb daytime heat slowly, keeping indoor air temperatures stable and comfortable for hours after outdoor temperatures have peaked. Interior temperature swings in high-mass buildings are typically just 3 to 5 degrees Fahrenheit, compared to 10 to 15 degrees in conventional lightweight construction. The reason for this is that the material acts like a battery. It absorbs the heat during the day, then releases it at night when it can be flushed out of the building. For new builds, the highest performance option is utilizing earthen building materials like cob, adobe, rammed earth, or hempcrete. These materials combine high thermal mass with natural insulation, moisture regulation, and low embodied energy. Hempcrete, for example, has a specific heat capacity of 1,000 to 1,700 joules per kilogram Kelvin, rising to over 2,900 at high humidity, providing thermal mass that actively responds to moisture conditions. Water also has an exceptionally high specific heat capacity at 4,184 joules per kilogram Kelvin, allowing water-filled systems to provide equivalent thermal storage to concrete in 1/3 of the structural volume. For retrofitting, there are several options at different levels of effort here. At the simplest end, removing carpet to expose an existing concrete slab, adding tile or stone flooring, or leaving masonry surfaces uncovered in rooms that receive afternoon sun can all increase the effective thermal mass of your home at minimal cost. A step further is a drum wall. 55-gallon food-grade barrels filled with water and painted matte black and stacked behind a south-facing window. So materials with a high thermal mass can trap unwanted heat, but night flushing, the act of discharging unwanted heat gain during the cooler hours, is the key mechanism behind these designs. The American Institute of Architects states that in dry climates with a day-night temperature swing of at least 20 degrees Fahrenheit and nighttime temperatures at least 10 degrees below the desired indoor temperature, night flushing with adequate thermal mass can create indoor temperatures comfortable enough without any active cooling at all. But any home can benefit from it immediately, regardless of construction type. A study published in Applied Energy found that night flushing reduced peak cooling load by nearly 36% in lightweight structures. And interestingly, the reduction was greater in lightweight envelopes than in heavyweight ones, because the lighter structures release their stored heat into the night air more readily. The advantage of simply incorporating the routine of night flushing into your daily routine can be huge. In dry climates, this practice alone often delivers 20% summer cooling savings at no cost whatsoever. In hot and humid climates, where the day-night temperature swing is small and nighttime humidity is high, night flushing is less effective and can import moisture into the building. But for hot, dry, Mediterranean, and temperate climates with meaningful diurnal swings, this is one of the most powerful and accessible tools available. And while constructing with earthen materials is a brilliant way of utilizing thermal mass, the greatest thermal battery of all is the one below our feet. At a depth of 5 to 10 feet, the ground maintains a remarkably stable temperature, typically between 50 and 73 degrees Fahrenheit year-round, regardless of what is happening on the surface. Through the use of an earth-to-air heat exchanger called an earth tunnel, we can utilize this temperature difference. A buried pipe network pulls outdoor air through this underground thermal reservoir before delivering it indoors, giving up its heat to the surrounding soil before arriving significantly cooler inside the building. And the impact of these simple systems should not be underestimated. A Natural Resources Canada field study in Toronto measured a summer air temperature drop of 12.2 degrees Fahrenheit, while the 29-story EPCOR tower, using nearly 3,000 feet of subterranean pipe, reduces annual HVAC energy costs by 23%, saving approximately 50,000 Canadian dollars every year on cooling costs. Earth tubes are powerful tools for cooling interior buildings, but installation is the big barrier here. A properly designed system requires 6 to 8 inch HDPE or PVC pipe buried 5 to 10 feet deep, running 100 to 165 feet in total length, with a continuous drainage slope of 1 to 3% to prevent condensation and mold, which can be a dangerous problem in poorly designed systems. In new construction, where the excavation is already happening, this costs $2,000 to $10,000. But retrofitting an earth tunnel to an existing home is significantly more difficult. A related technique to the earth tunnel is earth coupling, where concrete floors, and sometimes walls, are placed in direct contact with the earth. At the stable ground, temperatures found at moderate depth, an earth-coupled slab acts as a passive heat sink year-round. Earth-sheltered homes are the extreme of this principle, with fully bermed homes achieving up to an 80% reduction in combined heating and cooling energy. But the final and most crucial heat removal method for any passive cooling system is the use of natural ventilation. Natural ventilation uses wind pressure and temperature differences to drive airflow through a building without mechanical fans. Moving air does not significantly lower the dry bulb temperature of a room, but it directly cools the occupants, disrupting the boundary layer of warm, humid air clinging to the skin and enhancing the body's rate of evaporative cooling through perspiration. This is an important distinction, as the cooling effect on the skin is equivalent to a 3 to 5 degree Fahrenheit drop in air temperature. Cross ventilation is the simplest form of natural ventilation. Air enters on the windward side and exits on the leeward, effective to a depth of roughly 5 times the floor-to-ceiling height from the inlet. Incorporating a well-managed cross-ventilation system into your home can reduce indoor air temperature as much as 9.5 degrees Fahrenheit. Building orientations and interiors designed with this in mind will be much more efficient, as room and window size, door placement, and window types all play a role. However, maximizing the cross-ventilation of your existing space is certainly possible by utilizing a floor plan that allows for unobstructed airflow, as well as fitting styles like the louver or jalousie windows that allow wind to pass through almost 100% of their physical opening. Besides cross-ventilation, you can also utilize stack ventilation. This works on the principle that warm air rises and exits through high openings like clerestory windows, operable skylights, or roof vents, while simultaneously pulling cooler replacement air in through low-level inlets. The outlet needs to be at least half a story above the top ceiling for effective buoyancy-driven flow. For retrofitting an existing property, the most accessible options are ridge ventilators or turbine ventilators installed at the roof peak. Balanced soffit and ridge venting, cool air entering at the eaves, hot air exiting at the ridge, can reduce attic temperatures by up to 50 degrees Fahrenheit. The building code rule of thumb is 1 square foot of net free vent area per 150 square feet of attic floor, split roughly 50-50 between intake and exhaust. For new builds, the most advanced version of stack ventilation is the solar chimney, a sun-heated dark vertical shaft that drives continuous upward draft, creating a sustained low-pressure zone that pulls warm air out of the living space and draws cooler replacement air in from below. A 13-foot-tall vertical solar chimney with an air cavity width of approximately 8 to 12 inches generated average air velocities of approximately 1.5 to 2.5 feet per second at the outlet, more than sufficient for indoor air renewal. In experimental evaluations, solar chimneys generated indoor air temperature reductions of approximately 9 to 10 degrees Fahrenheit. And when connected to earth tubes at the inlet, heavily inspired by the Persian Badger and Connaught system, the chimney's mechanism becomes even more effective, pulling pre-cooled air through the subterranean network and distributing it throughout the house without consuming any fan electricity. Now, unless you are planning to build a new home from the ground up, many of these techniques may not apply to you directly. For most existing single-family homes in hot, low-humidity climates, areas with meaningful summer heat, and a reasonable day-night temperature swing, the highest impact, lowest cost combination follows the same 3-step hierarchy this video has laid out. Start with heat control. Bring your attic insulation up to code, add a radiant barrier, and recoat your roof with a high reflectivity white paint. Together, these address the single largest source of unwanted heat gain in most homes at a combined cost of roughly $500 to $2,000. After this, shade your west and south windows with exterior awnings, solar screens, or exterior shutters, and keep them closed during the heat of the day. Apply a low emissivity solar control film to any remaining exposed glazing, particularly on east and west-facing windows where low-angle sun is hardest to block. Next, you should address heat reduction. Plant 2 to 4 deciduous shade trees on the east, west, and northwest exposures of your property. At $50 to $300 per tree, with documented cooling energy savings of 30%, this is one of the highest return investments available, and the benefit compounds as the trees mature. Alongside the trees, replace any dark paving around the house with light-colored pavers or ground cover planting. If you are in a dry climate, consider adding a water feature, even a modest courtyard pond or fountain, to the area immediately adjacent to your most sun-exposed wall. Finally, dissipate what remains. If you have a concrete slab under your carpet, expose it. If you have tile or stone floors, leave them uncovered in rooms that receive afternoon sun. These surfaces will absorb daytime heat and stabilize your interior temperature swings. Consider the optimal interior arrangement, window openings, and window types to maximize cross-ventilation. Use a stack ventilation method too, whether that is a ridge ventilator, a turbine vent, or simply a high-mounted operable window, to allow hot air to escape from the highest point of your home. On top of all these modifications, the easiest, no-cost win is to make regular use of night flushing. Seal your home during the day and open windows when outdoor temperatures drop at least 5 degrees Fahrenheit below indoor. In dry climates, this practice alone often delivers 20% summer cooling savings. Of course, there is no one-size-fits-all passive cooling solution. The right combination depends on your local climate, seasonal temperatures, humidity levels, and the orientation of your land and property. And while it may not be as efficient as designing a passive cooling system into a new build from the ground up with consideration of solar orientation, the combination I've just mentioned routinely delivers 25 to 40% cooling energy reductions in field studies at the cost of just a few $1,000s. Passive cooling is not a single technology. It is a hierarchy, a sequence of interventions that work with the physics of heat rather than against it. If you enjoyed this video and want to learn how you can make your home more self-sufficient and less dependent on centralized infrastructure, then why not consider subscribing to our channel?